Welcome to class. In the last video, we talked about what solutions to differential equations are, and that's going to be really important for this section. So if you haven't watched the last video, or if you're not familiar with the topic, I'd recommend you start there. But in this video, we're going to be talking about how do I model with differential equations. So far, we've seen what differential equations are, and we understand a little bit about how they work, or at least what a solution to such an object would be. But I think a really important scientific and mathematical question to ask is, why should I care about them? And we're going to answer that question in much more detail throughout our course, but I at least want to give you a little bit to latch onto for some motivation to push forward. So in this section, we're just going to look at a couple of examples of how I might model a real-world scenario using differential equations. And a simple application space we can look at is population growth. Now, we know from biology that the population of a species, P, grows proportionally to, well, the population. In other words, the more members of a population there are, the faster the population grows. And this can be translated into a simple differential equation, because we've learned in our Calculus 1, 2, and 3 classes that derivatives are the language of rates of change. So when I talk about a population growth rate, really what I mean is dp dt, or the derivative of the population with respect to time. And that certainly depends on P, but when I say it grows proportionally, it just means that it might not be literally that dp dt equals P, but it's that up to a constant, maybe K. So here's an example of a simple real-world scenario that can be modeled using differential equations. Let's take a look at some more interesting ones. In epidemiology, we can also model the spread of a disease using differential equations. For example, if I call I the infected population, and I call H the healthy population, we know from epidemiology that the growth, or the spread, really, of the disease is proportional to both of these things, to I and H. This stands to reason, essentially, the more people are infected, the more virus is out there, so the disease spreads faster. Additionally, the more healthy people there are, the more hosts there are for the disease to spread to. So the more healthy people and the more infected people, the faster the disease spreads. And in fact, that compounds. If there are a lot of infected and a lot of healthy people, then the growth rate gets even larger. So in this case, we would say that the spread of the disease, or in other words, that's the rate of change of my infected population, is dependent on simultaneously how many infected people and healthy people there are. But of course, it might not just be literally equal to. I may have that statement up to a constant K. An important application space to both chemistry and engineering are mixture problems. And these ones can be a little tricky to think about because you have to think about them in terms of ratios. Essentially, a mixture problem would involve wanting to keep track of M, or the mass of a substance in a mixture. But of course we know, sort of from common sense, that the change in mass as you mix your solution is proportional to a couple things. Well, it depends on how quickly you're adding, and how quickly you're removing that substance. To give you a picture to think about, suppose you've got some tank and it's got some fluid in it, and you're adding to that fluid a solution, right? You're adding a solution. Let's just say maybe it's salt brine. And inside the solution, you're thoroughly mixing it. We won't worry about what happens when you aren't thoroughly mixing it. That's a much tougher problem. So you mix it up in there, and then you pour some of the solution out, right? You're draining it out of the tank. And in this problem, it would be helpful to know how much salt is in the tank at a time. Well, surely, from our common sense, we can start by writing that the rate of change of the mass of salt, is the substance we're tracking this time, is certainly equal to at whatever rate it's being poured in at minus whatever rate it's being poured out at. But the actual dynamics of what describe R in and R out may differ depending on the problem and depending on the concentration of your solutions. The last application I want to look at in this video are falling bodies. So, to be clear, this means I've got some object and I drop it. We're going to ignore air friction for now, meaning there's only one force acting on this object, and that's the weight of the object, of course, pulling it down to Earth. Newton's second law tells us that the net force is equal to the object's mass times its acceleration. We can actually write this as a differential equation, though. We know that its net force is equal to its weight, in this case. That's the only force, and it's pulling the object down. So, if I set up a reference here, we usually like to call up positive, and I'll use h for height, and down negative h for height. So, in this case, I've got weight acting in the negative direction, and we know that its weight is going to be negative mg, where g is the acceleration due to gravity on Earth. On the right-hand side of the equation, we can write the acceleration as the second derivative of its height with respect to time. Cleaning up the m on both sides, we get that g equals d squared h dt squared. And here we can see that Newton's second law can often be written as a differential equation.